Hey, hello. So today we're going to be talking about sandboxes. We're going to be going through a couple of the main techniques for how you might use sandboxes, how you might get started, when you might use them. We're not going to be doing a deep dive today. There's too much to go through. So this is very much a whirlwind tour. Hopefully by the end of this you'll have enough to get started. So let's jump right into it. First, by way of quick introduction, hi, I'm Tom. I do security. I've been working on platform containment stuff for the better part of a decade. So why do we care about this? Why do we care about platform containment? Why do we want sandboxes in the first place? If you go and have a look through, with a magnifying glass, the kind of work you'll do on a computer, whether it be as a developer, whether it be as an analyst looking at perhaps reverse engineering, or even just personal life admin, there's plenty of opportunities for initial compromise. For the most part, we like to think about our workflows as being fairly secure, and that's generally true. But sometimes in your threat model, the reality exists that things happen, and you might get popped. Sandboxing is the tool in our platform containment toolbox to try and control that risk, to put a boundary around what can happen, and really give us some guarantees there if the worst case does happen. And just to really drive home like this possibility, let's look at a few workflows. Let's imagine you're an analyst. Maybe you are looking at some binary. You're running strings on it. What's the possibility that that binary was meant to run into that input, into strings, and actually exploit some vulnerability and take over your machine? Similarly, browsers. Browsers run JavaScript. At this stage, that's basically native code. Granted, there are tons of sandboxes. The possibility exists for it to do a lot more than you intended, and you're going to have to work through your threat model for this. And lastly, of course, is workload compromise. If you're running something in a container, chances are there are open source components. There are components that you didn't audit. And what are the possibilities that that is compromised? Can then access the data on your system, perhaps exfiltrate credentials, and from there, all bets are off. So platform containment, and specifically sandboxing, which is what I'm going to be talking about today, are the tools we use to try and control that blast radius. It's the tools we use to try and give us some guarantees, so even if some element of our system, our workload, is compromised, we still control access to something else, or such as preventing it from laterally moving, preventing it access to credentials, or that kind of thing. So I'm going to be going through three kind of broad techniques today. First one being kernel-based sandboxing. That's where you ask the operating system to help out. That's things like the technology underlying container runtimes, Linux namespaces, Linux security modules, and the like. The second broad category is system call emulation. This is things like gvisor, and it provides a bit of a better security guarantee than kernel-based sandboxing, and I'm going to be going into the downsides a little bit more later. And then the last one, which I hope to spend most of my time here today talking about, is virtualization. How we can use virtual machines to really provide a strong security boundary between workloads and the host and everything else. Technologies in this category include a lot of the Rust VMM virtual machine manager ecosystem, so tools like Firecracker and Cloud Hypervisor. And there's also some work to integrate this with the container ecosystem, so things like Kata containers. So let's talk about the first category, which is kernel-based sandboxing. And what's really useful here is to look at it from the perspective of the normal, like a normal process, and then also from the perspective of a sandboxed process. So when an operating system starts a process, it first starts by hollowing out a bunch of memory. This memory is going to be used to store the data and the code of the process, and it instructs the hardware to map into this address space. To map that physical memory for that process into the address space. It's literally configuring the hardware. It then puts the CPU into an unprivileged mode and tells it to go, like go ham, go run this program. CPU in its unprivileged mode cannot do all that much. It can move data around, it can do basic arithmetic, it can do some bit twiddling, but just from that perspective with no further interfaces, the program can't do all that much. It's fairly well restricted to its address space. So then the next question is, well, how does a normal process actually get anything done? How does it do disk I/O? How does it interact with the network? That kind of thing. And the answer is this interface called system calls. Whenever a process wants to do anything, it's going to invoke a system call, which is its own instruction. And that's going to hand over control from the unprivileged process context to the privileged kernel or operating system context. From there, the kernel can go ahead and actually service that request, doing the network I/O, reading the file system, whatever needs to happen in order for the process to do what it needs to do. So with a sandbox process, knowing that, hey, everything that needs to get done that interacts with the outside world is a system call, there are some caveats there, but for the most part, anything that a process is doing is a system call. What if the operating system was involved in, hey, filtering out what resources a process can interact with? And that's the basis of all the mechanisms in this class. All kernel-based sandboxing is going to be applying some abstraction, some filter, in what a process can interact with. This can be as overt as blocking access or returning errors, or as subtle as simply returning less results or different results. This concept of returning different results to a system call is called namespacing, and we see this a lot, particularly on Linux. So yeah, if system calls are the interface to the process, then system calls can be used, and the filtering of system calls can be used for sandboxing. So how do we actually accomplish this? There's a couple of main mechanisms, and there's way too many to go into. Just on the slide here are a couple of the important ones. For instance, mount namespaces are what's used to isolate the file system for a process. So let's say you want to run some process, you want to give it a different view of the file system, you can launch it into a mount namespace. From there, you could do something like bind mount different directories into that namespace, and then whenever the process attempts to interact with the file system, it'll see that different view rather than whatever the system by default sees. A good example of where you might use this is for piecemeal isolation of certain directories or resources. So by way of example, if you want to stop /root/.ssh, you could bind mount inside that namespace a different file over there. The process will still be able to read it. It'll still be able to execute those instructions and get the results back from the system call, but it'll be for the namespaced file system. So you'll be able to give it different results and not compromise your credentials. Similar things exist for network namespacing. You can launch a process with a different network namespace, a different set of network interfaces, and apply different, say, IP tables, NF tables rules, allowing or preventing access to certain addresses. And there's tons more mechanisms. PID namespaces, UTS namespaces, things like seccomp filters. We're not going to go into them today because there are literally dozens. So yeah, how do we actually do this? If you want to learn how this works under the hood, as you can tell, it sounds fairly involved. I do recommend Googling containers from scratch, a fantastic tutorial, and that will walk through the process of actually setting up and running a container using all these mechanisms. But if you want to actually get stuff done quickly, I recommend using FireJail. FireJail is a fairly straightforward application where you provide it configuration for all these namespaces and for all these restrictions as basic text files. So things like, I want this file to be accessible at this path for the process, or I don't want this file read-write, that kind of thing. As you can see on the screen, the example here is just running FireJail by default, which for me launches just bash, just a shell. But despite looking to the shell like it's running as root, there are actually a ton of restrictions applied. It's got a restrictive seccomp filter. It sees a different view of the file system. It even sees a different view of the user and the user mapping. So in this case, user 0 root is mapped to me, which is user ID 1000. So this all sounds pretty good, but it does have some downsides. The main one being we are relying on the kernel. We are relying on the operating system to get this right. And in practice, it doesn't always do this. In practice, when we rely solely on the kernel to restrict a process interaction to the outside world, there's usually some escape, there's usually some exploit, and it doesn't work as well as we would like. We can speculate as to why this is. I'm going to try not to do that. It might have something to do with being a very large attack surface, hundreds of system calls. It might have something to do with being in a memory unsafe language. Regardless, kernel-based sandboxing on its own doesn't provide the security guarantees we would like unless you're really dealing with low-hanging fruit. So it's better to chain this technique with other techniques that I'm going to talk about later. Speaking of which, system call emulation. If we can't trust the operating system to do this kind of syscall filtering, what if we introduce a purpose-built boundary that does this kind of filtering of system calls and analyzes them to make sure that it's able to access the correct resources and not accessing something that it shouldn't be. We can build this boundary. We can build this boundary purpose-built using modern software practices and do a good job at creating a solid security boundary. And this is things like gvisor. Gvisor is really good at this and generally recommended for things like container workloads, particularly for server workloads. It does have a few downsides in that, as I mentioned before, it is a supervisory process. It does have to handle all of the different syscalls that might be issued. And as you can imagine, there's hundreds of syscalls. Not all of them are implemented. As a result, it doesn't work for absolutely everything. It does tend to work for most server workloads, things like web servers, databases, and that kind of thing, but not everything, and you just have to try it out with your workloads. The other downside is because it is ultimately another layer between a process and the kernel. It does have overhead, and this is particularly noticeable for I/O-heavy applications. So let's talk about virtualization. Virtualization is where we take not only the processes we want to sandbox and put them in a security boundary, but a whole other system, a whole kernel, and all the virtual memory and all the virtual CPU associated with a virtual machine. We put that in its own box, and then we defend that boundary with the host. Despite what you might think, this does look complicated, but it actually ends up being a smaller attack surface to defend. The interface between a virtual machine and the host machine is mostly just some basic primitives. You need the ability to have disk, so that's reading and writing bytes at certain offsets. You need the ability to typically need the ability to send network traffic, so that's reading and writing Ethernet frames. That kind of send-receive interface we can build pretty easily and be fairly confident that we've done a good job. So that, compared to implementing every system call, ends up being a much smaller attack surface that is much easier to defend. As a result, in the last few years, we've seen a lot of development in this space, people building virtual machine managers as security boundaries that are able to run virtual machines, provide this interface, and do a good job at securing them at this boundary. There is a downside, though. You've got now a virtual machine to deal with. It's not just a process where you're launching some arguments and wiring up, standard input, output, or network. You also have a full virtual machine. You've got to pick the kernel. You've got to configure it to start up and start your workload, and that's a lot of work. That said, there are a couple of VMMs that have sprung up in the last few years that are pretty good to help you orchestrate this, and we're going to use Firecracker as an example. So Firecracker I really like because it's made by AWS, it's used for Lambda, it's fairly well battle tested. It's also very easy to get started with. You pass the kernel image, you pass the init basically any devices you want on that system. So it could be a file system, it could be network devices. You configure that as a config file, and then you run Firecracker. It could be just another process. You could also apply some of these other techniques to it. You could use kernel-based sandboxing techniques to manage the network and that kind of thing. But as I mentioned before, integration is really the hard part for VMs. You need to make that system image. Maybe you start with something like Alpine Linux and then modify init scripts and that kind of thing. But you still have to think really carefully about it. There's no point in having a VM as a security boundary if you just put the entire file system of the host into that VM. So then any compromised workload on that VM can just modify your file system, read your secrets, establish persistence. Similarly, if you're worried about network access, probably don't just bridge the VM's network interface with that of the host. You want to apply some kind of restriction. And when and however you apply that restriction, it must be outside of the VM boundary, because we're treating the entire VM as your security boundary, and anything inside it, including the kernel, could be compromised. Other thing worth mentioning, if you're trying to sandbox a client workload, maybe you're putting the Tor browser in there. Think carefully about the user experience. Does this browser window look like any other browser window on your host? Does the possibility exist for you to accidentally copy-paste something really bad into the wrong context and OPSEC fail that way? If that's catastrophic, think about how you're going to separate the two and how you're going to avoid human mistakes. Because as you start to move towards the more restrictive side of sandboxing, you start to see OPSEC failures be a main source of compromise. So let's walk through a little bit of an example here. Let's say you wanted to play around, you wanted to have an environment where you can just kind of play around with stuff from GitHub. Maybe on the training page, maybe you see AutoGPT or whatever, and you just want to mess around. You don't want to think about whether there's a dependency that's compromised. You don't want to think about whether it's going to take over your machine. You want it to stop when the VM stops, and you want it to avoid stealing all your credentials. One way we could do this is make a VM for it. So we'd go through the effort of picking a VM image, such as Alpine Linux, and modifying it to boot up our workload. In this case, establishing a CLI. Wiring up that image is fairly straightforward. We pass it in as a block device in the config file for Firecracker. But then we need to create some interface where we can run that command, where we have a shell. To do that, we can use this mechanism called a VirtIO socket. And this is basically a really efficient socket between a virtual machine and its host. And it's yet another element in the config file. It's fairly easy to set up. Inside the VM, we would wire this to, say, bash. You could do that in a systemd unit. Outside the VM, we'd wire it to standard in, standard output, just as a socket, maybe using Netcat. And then lastly, we'd need some way to get internet access within the VM. This can be, as I mentioned, all the restrictions you're applying need to be outside the VM's boundary. Otherwise, a compromised VM can just remove them. So in this case, we want to do the networking restrictions outside of the VM. This is a really good example where you can stack some of the techniques. In this case, stacking VM-based isolation with kernel-based sandboxing. The way you do that is just take the virtual internet or the virtual Ethernet adapter that comes from Firecracker and put it in its own network namespace, and then apply those restrictions accordingly. Maybe using IP tables rules, maybe using NF tables, whatever. Restrict it so that it cannot access any of the private network interfaces, addresses, or your local machine. This all sounds like a lot of work just to spin up a VM, and that's true. This is quite a challenging, sandboxing workloads in VMs is quite challenging because of this integration work. I'm trying to work on a project to make this easier, so you can just pass in a list of packages, what kind of network restrictions you want, and it'll orchestrate all of that for you using Firecracker. If you're interested in something like that, please check it out. GitHub.com, twitchyliquid64/minikernel. But yes, this is one of the harder parts of using VMs. So let's put it all together. We have three main techniques we've talked about today. Kernel-based sandboxing, which is perhaps the easiest to deploy, but also doesn't really give you the security guarantees you want on its own. Syscall emulation, which is good for server, particularly container workloads using gvisor, but does have performance limitations and doesn't work for everything. And then virtualization-based sandboxing. Perhaps the strongest of the security boundaries, but is also quite challenging to set up in terms of integration. Regardless of what you choose and regardless of how you choose to set up your sandboxing, always start it with a threat model. You want to understand what you're defending against and also what you're not defending against. And then from there, you have a good idea of what to deploy and where. Cool. Questions?
Thank you so much. All right. I'm going to run around to you with hot mic. Please hold. So first question is up in front of you to your left.
Hey, I don't know what Twitchy Linux is, but it sounds cool. Would it by any chance use any of this kind of sandboxing stuff?
So Twitchy Linux is my pet Linux distro that is also on Nex, and unfortunately it does not use any of this sandboxing. Side note though, a lot of what I'm talking about here with sandboxing is about sandboxing workloads. When it comes to trying to sandbox a general purpose environment, it doesn't work so well because different programs need to do different things and access different resources legitimately. As a result, general purpose sandboxes don't do such a good job at restricting everything you need compared to more specialized sandboxes for specific workloads and specific tasks.
Other questions? Raise your hand high.
Hey, nice talk. Thank you. I guess another option on that is to get the VMs off the shelf from your favorite cloud provider. Do you want to respond to that a little bit? Fit that into the model?
Yes. So I guess if you don't want to do the work of integrating and running it on your local machine, you can always orchestrate using something like GCP or using AWS or using Cloud Run. This is a really good option as well. Certainly when I was at my previous job, we did exactly this. We had a shell by which you could run risky commands with no privilege, and we called it Red Shell. So that's certainly a very viable option as well.
We've got time for one more question if we've got one more question in the audience. Awesome. One more round of applause, please, for our presenter.